So here's the problem. Figure out the strength of the magnetic field outside of a wire, current carrying wire with a radius of capital R. All right, so here's the current carrying wire. This is the radius of R, capital R. We're interested in the strength of the magnetic field at a radial distance of lowercase r. So figure out the strength of the magnetic field at a distance of lowercase r, which is going to be larger than capital R. All right, so we're using the Ampere's law. Notice that the vector B and ds, they're going to be in the same direction. All right, so the angle is going to be 0, cosine of 0 is going to be 1. So all of a sudden we are able to express the vector dot product in terms of a scalar multiplication. All right, so here ds is going to be the same as the circumference of the wire, which is going to be 2 pi r. So we'll do a back substitution and then become the expression for B outside of the wire. Magnetic field strength outside of the wire. All right, now this is the extra credit problem. Okay, so we got two parallel straight wires. Current is going to be coming out of the page in one of them, and current is going to be going into the page in the other, and they're separated by a distance of r. It says you will have to use the Ampere's law at least once for one of the formulas. So here's the extra credit. That's the current element coming out of the page. The second one is going into the page. So here's the magnetic field. Here's the magnetic field generated for the first current element. By the first current element, R is the separation distance between these two wires. All right, so the magnetic field due to the first current element acting on the second current element at this location. Remember, the current is going into the page. Let's apply the right-hand rule number 2 to this. Number 1 to this, and immediately you'll notice that the force is going to be to the right. Magnetic force acting on the second wire due to the first wire is going to be a repulsive force to the right. Let's write out the formula for it. All right, so sine of the angle is going to be, this is the angle between the direction of the wire, which is going into the page, and the magnetic field, which is in the opposite direction. So the angle is going to be 90 degrees. Theta is going to be 90 degrees, so sine of 90 is going to be 1. So this expression is going to get reduced to this expression that we're looking at. All right, so now we need to figure out we need to come up with an expression for the magnetic field due to the first current element using the Ampere's law. This is 197 using the Ampere's law. All right, so magnetic field is in this direction, so this is a vector, and ds is also in the same direction. So this is the same as the previous problem. So we have to come up with, this is a vector dot product expression that needs to be expressed in terms of a scalar. So the angle between d and ds is going to be 0. All right, so cosine of 0 is going to be 1. So this entire expression that we came up with, the vector expression, can become a scalar expression. All right, so ds here is the same as the circumference of the wire, circumference of the circle, in this case, not the wire. All right, so now isolate the magnetic field due to the first current element. And the only thing we have to do is just grab this term here and then substitute into that one. And that's the conclusion.